properties of the device. And if we do that, it's really a scattering problem, or in the language of quantum particle theory, it's a transmission problem. It's what is the probability of the electron can be transmitted from one end of the junction to the other end of the junction. And it is also a non-equilibrium problem because you have to drive it with some kind of a voltage. So you have to drive it with a current flowing from one to the other constantly. So it's not equilibrium. At equilibrium, there's no time to exit current. Right? So that's the basic parameter of the problem that we're looking at. And I said that we want to generalize in the type of generalized Landauer formula to finite-bias. So we need to understand what Landauer formula is. So let me give you a very quick introduction to Landauer formula is. So consider a nanoelectronic junction. Here I put in a typical molecular junction here. And I want to put two electrodes. So this is basically benzene ring. And then I attach the benzene to two gold electrodes to sulfur atoms. So this is a very standard molecular junction. And I want to connect it to two electrodes with two different chemical potentials. So if there have an imbalance of chemical potential, obviously the system is non-equilibrium, I would have a current flowing from one end to the other. So the chemical potential for this side is higher on the left, I call it mu L is higher than the chemical potential mu R on the other side. And therefore the electron would run through the junction and to the other side, and not the same number of electrons can run back. So below this mu R, the number of electrons running both ways is the same. They cancel each other with current. But above mu R, because there's no chemical potential, no electron above that chemical potential, the electron can only run one way, so you have a net current. And so just based on counting the number of electrons, we can sort of derive, if we want to call that derive, that's what we call heuristic derivation, derive the Landauer formula, just by counting the number of electrons running through. So how do we count? All right. Each electron would contribute a current that's E times VF. VF is the, I should just call it the electron velocity, Fermi velocity. Okay. But not all the electrons can run through because T is a transmission probability. So if the transmission probability is 50%, then half the electrons can run through, the other half gets reflected. So you multiply by that probability, and then you multiply by the number of electrons available to transmit. And that's what we call delta rho. That gives me the total current. So we need to find what delta rho is. Once we know what delta rho is, we know the full answer. So what is delta rho? And here we need a little bit of quantum mechanics or solid state physics here. So delta rho is the N, which we call it the density states. That's just the number of electronic states available in unit volume, unit energy interval. Multiply the energy interval from mu R to mu L. So the region of the energy that's under non-equilibrium condition. So that this is a potential difference multiplied by the electron charge. That's the energy difference. And the density states. This is simple quantum result, simple solid state result. Density states is essentially 1 over the electron velocity times the h, which is Planck constant. So it's basically quantum mechanics result. So that's the number of electrons available for transmission. You plug this into that equation, immediately comes out the conductance, which is defined as the current divided by the chemical potential difference, which is E squared over H times transmission probability. So this is the famous, well, actually we call it Whittaker formula. It's actually derived from the extension of the Landauer formula. This is the Whittaker formula that's used everywhere in quantum transport theory.
But shouldn't it be in general be a function?
Yes, exactly. Very good question. here we ignore the dependence of VF, eccentric density space, as a function of the energy or bias voltage, which would be only valid in the case of infinitesimal bias voltage. So this is, in other words, this result is a linear response result, a zero bias result. That's why our result in a few slides down will be a generalization of this result to finite bias. So if this result is rigorous, there wouldn't be talk today. My talk should not exist. So thank you for that, bringing that up. Yes.
So how is the transmission probability be calculated? Is it calculated by treating the entire intermediate region as a autonomous variable?
Yes. Transmission probability is calculated by simply calculating solving the Schrödinger equation for this whole problem, and then finding out what is the so if you have an incident boundary condition, incident electron wave function coming in this way, what is the probability that you get some electron wave function going that way? So that there is this is a sort of a standard quantum mechanical problem. So you basically converted the problem calculating conductance into the problem calculating transmission, which in turn is a quantum mechanical problem. Then we can actually use what we call the first principles method to do this calculation. All right, so that's Whittaker formula, that's not Landauer. So what's the difference between Landauer and Whittaker? Actually, that's the what's called a contact resistance. So Whittaker formula actually has this strange consequence. Think about perfect transmission. When you have perfect transmission, what do you expect the conductance of the material to be in the case of a perfect transmission? No scattering whatsoever. Zero resistance. Infinite, exactly. So the conductance will be infinite. Look at perfect transmission, T equals 1. What is conductance? E squared over H. It's not infinite. What's wrong? Because even when you have perfect transmission, you still have what's called contact resistance. And that is the difference between the Landauer formula and the Whittaker. So how do you count the contact resistance? The way you count it is by counting the amount of the electrons, excess electrons on both sides that causes the difference between the voltage drop and the chemical potential that you put in the reservoir. So on the left, for example, some of the electrons got transmitted. They don't get reflected. If all electrons are reflected, okay, so T equals 0, R equals 1, then the chemical potential and the electrostatic potential should agree with each other exactly. You should not have difference. But because some electrons are transmitted and they don't get reflected, so you're losing some electrons above mu r. So in that region, you have fewer electrons than the equilibrium case. So your electrostatic potential is actually lower than your chemical potential. And the amount it is lowered by is this amount. Transmitted, those transmitted times the difference in the chemical potential divided by 2. Because the transmitted still goes through this region this way, but there's nothing coming back, so you're losing half of the amount that you should be there. And on the right-hand side, you have extra electrons above the mu r due to those electrons transmitted. So your actual electrostatic potential is mu r plus this same term here. Okay, so you subtract these two electrostatic potential, and you get a voltage drop. And it turns out that voltage drop is not mu L minus mu r, the chemical potential difference, but rather it's 1 minus T times the chemical potential difference. And then you divide that to the current, you find the conductance after the contact resistance correction is the quantum conductance times T minus over 1 minus T. This is called the Landauer. And in this case, you have the expected result when T equals 1, the conductance is infinite. Okay.
So this Landauer one is actual analog is Boltzmann field is the steady state distribution. So you are counting in the presence of the bias or as the electron redistributed.
Right, except I'm doing everything in the ballistic limit.
Yeah, exactly.
Right, so in the Boltzmann theory actually is not the ballistic limit, it's actually the diffusive theory. Or it's a somewhere, a semi-diffusive theory.
Yeah, I'm just saying that
Yeah.
as analog, you can put in the steady state distribution, not the original equilibrium distribution.
Okay, yeah. So, no, the contact resistance is actually literally the contact resistance. So it's the, so every resistance has a ohmic dissipation. So it actually dissipates heat. And if we assume this whole molecular junction is dissipationless, completely ballistic, you still have a resistance. And where does that heat dissipate now? Where is that dissipated now? It's actually dissipated in the electrons. So the electron runs through here, and then it has higher energy than the chemical potential. Then it dissipates energy and drops down to that chemical potential. So that's where the heat is dissipated. And that's exactly what contact resistance is. Okay. Yeah.
So this is usual one-dimensional derivation.
Right.
Fine, it's per channel. If I have a three-dimensional system, and so I have a parallel wave vector, then I can add up the channels.
You might, but there's a very interesting paper actually written by Whittaker and his coworkers that got very little attention, that the three-dimensional solution is not unique. And so even though you can put in the requirement of momentum conservation that we were talking about earlier, and all that, you still do not know what the correct answer is. It turns out the correct answer depends on the experimental setup. It depends on how the electrodes are coupled to the quantum channels of the device. And each different setup is going to give you a different answer. And it's been a long literature history of controversy about, because everybody has their own theory. And so you have very many different theories about multi-channel, three-dimensional Whittaker formula. And it turns out it's just because we have different boundary conditions. Yeah. But again, let me emphasize, this is just linear bias, linear response, zero bias conductance. And I'm going to say that in most cases, it's not enough because you want to know what happens when you go away from zero bias. For example, this is a somewhat older paper. I thought it was interesting. It's a carbon nanotube p-pop, and they're looking at this device where they actually have this kind of a, so you have a gate voltage here, and then you apply the source drain voltage here, and then the current is expressed as a color. And you can see that this is called Coulomb blockade diamond. So you actually have regions where there's just no current because of what's called the Coulomb blockade effect. And then you have regions, under certain bias and under certain gate voltage, you have currents. These conduction poles. Yeah.
So looking at that data, what is the first vacuum program? Or is that just the intensity?
First, this one?
Yeah.
Good question.
Second one, there is some intensity, but it's close.
Yeah, it's close, and this one is open. I don't know. I'm not going to model this. I just use it as an example. That conductance alone does not tell the whole story. And so what's useful here? This is actually this is not current. This is PIDD. Yeah. So this is a differential conductance.
And other people look at carbon without P-bonds and actually close that.
Yeah. Okay. That's interesting. All right. So differential conductance obviously is not the same as zero bias conductance, and so keep that in mind because that's the crucial difference that we're going to have to address in our new theory here. But I just want to bring up Here is a case, perfect case of, I don't know, light arithmetic in physics. You actually find this somewhere in history. That's exactly the same kind of a Coulomb diamond. This is actually a beanbag game, I think. Same color even. All right, so the important takeaway point here is that not only we want to look at the zero bias conductance, we also want to look at finite bias differential conductance. So how do we, theoretically, how do we calculate finite bias differential conductance, or how do we calculate the current as a function of bias? There is this famous method that everybody knows called NEGF or NEGF or whatever. It's called non-equilibrium Green's function method. It sounds really fancy and powerful and mysterious and deep. And I think the only people in this whole audience that understands it is probably me. Okay, then nobody understands it. But what is it? Well, let me say this. This is the equation I copied down from this famous paper, 1990 PRL, that formulated a solution for the non-equilibrium Green's function method. Starting from this formula, where V here are basically the coupling between the sample, whatever the junction we're considering, and the electrons. One connects to the left, the other one connects to the right. Well, actually, that's one of these ends, I believe. And the G lesser, the G with this lesser than sign on top, is called a lesser Green's function. It's one of the four so-called Keldysh Green functions. The other three, one is G greater than, obviously. If you have lesser than, you must have a greater than. And the other two are the normal, we call so-called retarded and advanced Green functions. And in the case of non-interactive system, this whole thing simplifies into something that we can better understand. That is the difference in the Fermi Dirac distribution function, or distribution function in the left and the right electrodes, times the trace of these products. Advanced Green function, retarded Green function, and then these gammas are the okay, so these are the advanced and retarded Green functions. And the gamma is the imaginary part of the self-energy due to the coupling to electrons. So I'm not going to go into detail discussing what these means or what they are, just give you an idea of how hard this problem is. Okay, the purpose of these equations are purely to scare you, so that you know it's a hard problem. You don't have to understand it. But let me note that this trace of G gamma is in fact sum over I Pi, where I is the channel number and T is the transmission. You can show that. So this is, for non-interactive systems, we can show this is actually the transmission probability. So this goes back to the Bunneker formula. If we understand that this is just a transmission, and then everything else is exactly the same as Bunneker formula.
So you're saying that when you go off from near zero bias, the only thing that's really changing is the transmission probability?
You're also changing the distribution.
Oh, and
yeah.
the application.
Right. Right. That is if you consider electrons as non-interactive. So if ignore the Coulomb interaction between electrons, which is kind of odd, but of course in mean field theory, that's what we do. Okay, to scare you a little bit further, how do we calculate the non-equilibrium Green's function solutions? One thing is, remember there's an energy integration in that integral is over energy. And integral over energy is not easy. Okay. Well, I think I got this out of order, but let me show this. if we had only the equilibrium Green function, Xiaoguang knows how to do that calculation. Because actually he's an expert on that. His LSMS actually does this Green function calculation numerically beautifully using this complex variable with integration. So this is counter integral. So equilibrium, you don't have this part, it's just this beautiful counter integration that makes it numerically robust and it's relatively easy to do, and it's a very mature technique. The problem arises if you have to do an NEGF. So I'm copying the same equation down again. Here's an advanced Green function. Here's a retarded Green function. I don't know how familiar you are with Green functions, but advanced Green function is only analytic in the lower half complex plane. And retarded Green function is only analytic in the upper half complex plane. Now, you multiply the two together, the product is not analytic in either half of the complex plane. So the only place where you can integrate this thing over energy is along the real axis. The problem is that we know if you integrate something that has a lot of structures in it along the real axis, you are not going to get anything reliable. It just doesn't work. So it's amazing that NEGF, this method, has been able to produce hundreds of papers every year with this tremendous numerical challenge built in. I don't know how they do that. Yes?
I think you're going to come to this, but like a lot of the NEGF calculations in literature, to my understanding, are not doing complicated energy. On a tight binding basis, NEGF just, as you know, gives you a way to couple in the incoming wave, and it's a big matrix.
That's at one energy.
That's it. Okay.
That's at one energy. If you want to know how the current changes with voltage, you will have to integrate over energy. If you want to know what happens at one energy, I'm going to add
So I take the trace of this big matrix, that's the inside thing.
That's inside the energy integration.
Okay.
Yeah.
And you're saying that that trace itself is fundamentally not so.
No, the trace itself is okay.
Okay.
It just gives you a lot of structure.
Okay.
Yeah, it gives you a lot of structure, and when you try to integrate over energy, you run into numerical difficulties. Okay, and it's amazing because I don't think people pay attention to that. Most people don't. They just take the code APK right now. So it's previously it's called a Trans-Fiesta. They just take it and run it and get an answer. They don't care about this, or they don't even know that. Okay, so let me summarize before I proceed. There's this integration along real axis that's numerically difficult. So that's actually the summary of the previous two slides. So what do people do? Instead of doing an actual finite bias calculation, they just take the EF and just move it to different energies and calculate for each energy, they calculate the transmission. That's exactly what you were saying. However, when you actually do that in the real material, you actually did that. You actually introduce space charge into the electrodes and into the material. You should be actually account for space charge, right, which people normally don't. And also you need to know that differential conductance is not transmission, and I'll show you that in a few minutes. So the real question, the question actually that all of this difficulties with, can we avoid doing non-equilibrium self-consistence calculation, because that's an awfully hard problem. And then the next question is, even if we can avoid that, there's also a question of converging the transmission, and this is a separate problem. In the transmission calculation, you actually have integration over k, the parallel k. And our experience typically takes at least 1,000 two-dimensional k-equals conversion calculation. And most people don't do that many. And you also have a problem with basis convergence. If you have a tight binding model, you actually don't know where the convergence is because you basically just arbitrarily truncate and then that's your answer. But that's an uncontrolled error. But if you were to use a plane wave basis, imagine you have to do trans-siesta and convert everything to plane wave and just do plane wave calculation for the IV calculation, and you have to run thousands of k-points for each energy point. It's a 9-8. Okay, so let me give you an example of how difficult this is, and I go back to the archetypical molecular electronics prototype, the gold benzene diethyl gold junction. This is a problem that a lot of people attempted. There's quite a few papers in the literature, and the problem is no one agrees with anyone else. First of all, there has not ever been any agreement between theory and experiment. And secondly, there has almost never been any agreement between any theory. Okay, so this is the very first publication of this junction. In 2000, that's a PRI on this paper is probably cited a few thousand times already. That's a subsequent calculation 2 years later. Exactly the same thing, same junction. Qualitatively different. In fact, you cannot tell, I mean, you couldn't have told anybody that this is the same junction. All right, and this is third one. I have to copy the figure from the paper, and so this all these are components contribution. You just look at the pink curve, which is total, and compare it. The only thing that you can see agreed is that the peak position agreed between these two calculations.
And if you say even in the first one, I can see two small peaks, general shape.
Maybe, but this is way too low. Right, so we have some serious problem here. And this is the finite bias. This is NEGF. So in fact, all these are NEGF calculations. This is trans-siesta. So all of these are NEGF calculations. And it just tells you how hard that calculation is. Yeah, so we have disagreement in IV and in zero bias conductance. All right?
I'm sorry, could you go on this? So the 40 microsiemens conductance, that's the like E-squared over H?
That's no, the E-squared over H is about 10 or so, I think. Is that right? It's 7.7. So this is several times of E-squared over H.
Also, I have a question about how do those people calculate the Lewis function? If they do band structure, they have to sum all the energies all the way up. How do they do it?
This is tight banding,
Okay.
so they can do the Lewis function pretty easily. This is actually, I can even understand. I mean, this is Radner's group actually, and they have their own code. They actually can do Lewis function. They could. I mean, they had Lewis function code for a long time. I don't know how they did that, because this is not plane wave based. This is probably also some sort of tight banding, because otherwise I don't. But they say they do CCSD, which is quantum chemistry code. I don't understand how they put CCSD and NGF together, but but this is a chemistry group.
The transistor should be unusual.
It is ab initio, but it's tight banding. This is not. This is actually they used the Lippmann-Schmidt equation. They actually just solved the scattering problem, and so they didn't use Green function. Okay, and let me knock the literature a little bit further. So because NEGF is so hard, this is actually a much bigger group of literature where you just don't do full IV calculation, rather you just do transmission as a function of energy. Okay? And I say, how about this picture? And I want to say, do you find anything wrong with this picture? So, for example, if you look at this point here, okay, suppose I want to look at, for this material, what happens here in the gap. My electrode doesn't have any state. If I put my Fermi energy here, the electrode doesn't have any state. It makes no sense. And so, it's, in this case, it's actually called electro-limited conduction. So what happens in the junction doesn't really matter anymore. You're restricting the conduction from the fact that you don't have any states in the electrode. And it's an interesting problem, but I don't think that's the problem that was intended in this paper. Okay. Again, I sort of forgot my slide off the order. So if you move the EF into the conduction band, for example, of the electrodes, you actually introduce the space charge in this case. If you use the electrode that doesn't have any space at the Fermi energy. And that's a nonlinear effect. And that's not intended, I don't think, in this kind of study. And I also want to make sure that you understand that differential conductance is not transmission. Here, we're calculating transmission and they're labeling it as G, as a conductance. But that's not conductance at all. And I'll show you the difference later on. All right, and this is a plot for the, I was talking about benzene diethyl. This is a plot of the historical values of experiment and theory. So the very first experiment was Mercury science article, and it's over here. Subsequently, people improved that measurement and showed, and these measurements actually were quite close to each other, considering how widespread everything else is distributed. So there seemed to be a reasonable agreement between the experimental value at this level. But the theory had been all over the place in the past few years, and our calculation actually is over here. So there may be a convergence of theory. But at least the theory and the experiment, if you consider them to be converged, is about a factor 20 apart. 25, at 25. So, yeah, so there's a big problem in here. All right, rephrase again. Non-equilibrium self-consistent calculation is tedious, it's numerically unstable, and convergence of NEGF is really hard. 2D K points, you need thousands or more. And basis, if you have a plane wave basis, it's large energy cutoff and large K points just make it terribly expensive. But if you use localized basis, it's uncontrolled truncation, so you don't know what to do at this point in order to get good.
Truncation of what? Spatial truncation?
Basis truncation. In other words, you don't have a complete basis.
I understand. Yeah,
Right. So
yeah, so you don't know what your error.
That's right. You have no idea what the error is. Yeah. And it's most apparent if you actually have tunneling problems. Yeah. Okay, so let's discuss how we generalize Landauer formula for finite bias, make it simple and easy and accurate. Okay. So again, it's just basically counting electrons. Instead of using counting potentials, I'll use the Fermi Dirac distribution function on both sides. And I rewrite the current as a function of transformation. This is a Bollinger formula, but instead of a mu difference, I have initial over energy and the difference between the Fermi Dirac distribution function. And so, of course, standard way of doing this IV calculation is using the NEGF method, but we're not going to use that. And we're just basically derivative this formula.
Just to clarify, what are the yellow atoms there?
Gold. Well,
So
these are gold, and this is sulfur, not sulfur.
Oh, okay. Okay. So there is a sulfur.
Yeah.
But the rest are gold.
Right. Okay, so I'm not going to go into details. This is formula we start with, and know that my transmission now has a dependence, explicit dependence on the voltage. So I take its derivative. I get this mess here. Basically, derivative of the Fermi Dirac distribution function with respect to the voltage, and also derivative of the transmission with respect to the voltage, two terms. And this I can evaluate using the so-called Summerfield expansion, pretty standard stuff. And I'm not going to bore you with the details. The answer is simple. It's just that. And it's the transmission evaluated at twice the applied bias voltage. This is an approximation. It's not exact, but it's a reasonable approximation. So this is basically, instead of putting on the bias for your calculation at whatever the voltage you apply and do the calculation, you actually apply twice the bias. Then you calculate transmission at the original bias window, two ends, and then you just add it to it, and that's what the idea. It's remarkable. It's surprisingly simple. Of course, it is an approximation, and I'll show you how good or how bad the approximation is. And this is we call it Fermi method. Actually, I'm running out of time. What's not the problem? So, no, well, actually, because I need to average over 2, there's 1/2 there. That cancels it. And I can go better. I can, instead of, this is actually the type of way to do the energy integration. But if I use synthesis rule, I get more terms. And then I have the transmission at the middle point in the energy. So that's the average of the two chemical potentials. So then I get a Messer expression. But I can use this to check my convergence. I can look at this and look at that and see how different they are. And then I have a good idea of the range of validity of this method. Okay, so how do I calculate at 2B? I have to calculate the electrostatic potential at 2 times bias voltage. And my first approximation is just making it a constant linear potential, which surprisingly turned out to be actually very accurate. But I can improve it. There's no need for SZ calculation. I can improve it by saying that if I have a dielectric layer here, my electric field should be proportional, inversely proportional to the density states at each point. So I just put down this equation. Local density states times the gradient of the electrostatic potential should be a constant. What it means is I'm treating the local density states as a quantum capacitance. So I have thin layers of capacitances in series, and that gives me this equation. Now, if, on the other hand, there's a lot of charge injection into the electrodes, then I cannot treat it as a dielectric layer. In that case, I have to take into account the excess charge that comes in from the tail of the wave function from the electrodes. And that comes from basically local density times this difference in the Fermi energy with the local electrostatic potential. And then I have to solve my Poisson's equation for that excess charge, and then I have to feed it back in there and iterate. Okay, so basically I have 2 cases I have to consider. One is the dielectric layer, no injection of charge, and the other one is a charge injection onto the insulating case. So the 2 cases I choose to test, one is my benzene diethyl junction, which I just showed you before, and the other one is a magnetic tunnel junction, which if I have time to cover, I can just do it quickly. All right, and the question is, I want to compare, I want to know how accurate my method is. So I have to have a way to get an accurate NEGF result, which I just told you that we cannot. So what do I do? What I do is, if I have a dielectric layer here, then I claim that my electrostatic potential is insensitive to the errors in my basis truncation. So I can actually calculate the non-equilibrium self-consistent potential from a transient stuff. Then I can take that potential and put it into quantum espresso, and then I calculate the transmission using plane waves. So then I get the best of both worlds. I get a non-equilibrium self-consistent potential, which transients I cannot calculate. And then I get plane wave basis for the transmission calculation, which I can control how well it's converged. And then I have an accurate NEGF calculation to compare, except this is a huge effort. And I only at the end, I only got 2 points. But and I can integrate the transmission over into the thing current. But 2 points after this, I'll show you what they are. But one thing we can do is to compare that transient self-consistent potential to the potential that I have by treating the local density states as quantum capacitors. And okay, this is my linear approximation. This black line is a transient self-consistent potential, non-equilibrium potential, and this red line is my potential using the local density states simple formula. So you can see how remarkably accurate my approximation is in this case for the potential. All right. So this is a calculation. These stars, these pink stars, are the NEGF full self-consistent calculation. Of course, at 0, we just know it. It's just zero bias conductance. But these 2 points are actually computed. And the black line is the 2V method, is the original 2V method where I only have the 2V terms. And the blue line is a 2V method with the Simpson's rule, so I have a higher order corrections. Okay. And you can see that the blue line actually goes with the stars pretty well. And so up this is 1 volt. I believe that even if you go higher, you still get pretty decent agreement. The black line, this dark brown line, actually starts to deviate at about 1 volt. That's a 2D method. So it's good up to 1 volt, and beyond 1 volt, you have a limited problem. And the green line is to use the zero bias transmission at different energies and pretend it's differential conductance. And you can see that for the most part, it's just off. Okay, and I just want to put it on the same slide with the other calculations, and you can see this one somehow doesn't make any sense. But this one, we got good agreement in the peaks and the top here, and almost the height, well, a little bit off. But then at higher voltages, we have some disagreement. Okay, one nice thing about the 2V method is we can easily add something like PFP plus U. And when we do that, we get this curve here that surprisingly the zero bias conductance goes way up. And it turns out that's about the same number that this group got using the GW. So who knows? Maybe we're not wrong. Let's go on to the next test case. And maybe a few more minutes.
Maybe 4, 5.
Okay. Yeah. So I want to say something about magnetic tunnel junction. Because we want to have not just one test case, but we ought to do a test case. So I'm not going to bore you with all the backgrounds. So this is the iron MgO iron tunnel junction, right? And so you have what's called spin filtering. So it transmits the S-type wave function much more than the P and D-type wave functions, and that's what the reason for a very large MR. Because when you flip the spin, this is when the 2 sides are aligned parallel. And when you flip the spin and they're anti-parallel, the S-type won't get through, so it's a spin filter. And that leads to a very large magnetic resistance. But what's interesting is we want to go beyond MgO. So let me just go through. So we want to look at some of these, what we call the cubic cation disordered crystals, CCDC. And so we look at these 3 different crystals. And what's interesting about them is that if your band gap is small and your barrier thickness is small, okay, this is the difference between an insulator and a metal, where in an insulator you actually have valence band completely filled, conduction band is completely empty, you have band gap in between. In the metal, the conduction band is half filled, and so if you have a band gap, it's way below the Fermi energy. The problem is, what happens when you put an insulator between the particles? Okay, this is a tunnel junction. A tunnel junction means the electron actually goes into the junction, exponentially decay into it. So it's not like that. It doesn't have a sharp interface like that. So what there is there's this exponentially decaying electron wave function. But then there's a problem. When you didn't have this part, the insulator is neutral. Now you put this wave function in there, this little bit of extra electron in there, it's not neutral anymore. And when it's not neutral, it's got space charge, it's got a local electric field. And that electric field will make your band gap bend. It's the same reason why you have a Schottky barrier. Okay? But here we have an ultra thin tunnel junction, and yet you get an arch band gap. And so we actually did the actual calculation. These are band structure calculations with all these different junctions, and you can see these arch band gaps as a function of different level of doping, and as a function of different materials. It's very interesting. But what's more interesting is if you put a bias on it, then these arch band gaps, they're going to get tilted. And what's interesting, you can see that one end of the, you can see this one end of it is pinned at one, and with one edge of the transport window, and the other end is pinned at the other side. It causes a highly nonlinear behavior. How nonlinear can it be? It is so nonlinear, actually, it turns out you get a negative differential conductance. So that's what's interesting here. So let me not go into detail on how we did the calculation and why this negative differential conductance is interesting. But let's just go right to the calculation. So I took the aluminum oxide result, which has the largest negative differential conductance at about 0.8 volts. And the pink squares are actually the numerical derivative of that IV curve. Okay, and it gets negative at this point. Now, our 2V method, because they're just sum of the two transmission, both transmission coefficients are positive, we will never get negative differential conductance. But amazingly though, we do get the overall trend. We get the conductance come down really, the differential conductance come down really low. And the 2V with the correction gets even lower. It never gets negative, which is disappointment, but I know that we cannot get everything, right? And compare that to the zero bias transmission as a function of energy, and if you pretend that's the differential conductance, you would get this curve, which is just completely wrong. So that's another reason why the transmission at zero bias as a function of energy doesn't tell you anything about the junction. It only tells you anything about junction at zero bias, nothing else. Okay, so you can actually get some temperature dependence, which it's a lot of math to work through. But the point is, the electron temperature actually has very little impact on IV. Most of temperature dependence comes from electron scattering, as you know. So this term actually you can just ignore it. It doesn't really matter. Yeah, lattice evaporation. All right. So summary. So we have this 2V method that allows us to do finite bias quantum transport calculation without an NEGF type self-consistency. And we get exit equilibrium with fully self-consistent NEGF calculation for the benzene diethyl. And the non-self-exclusive method allows us to include correlation effects more easily. Yeah, there's some unresolved questions. I really would like to acknowledge my group members, postdoc students, and also my collaborators. Thank you.